On March 20th, 2025, a team of engineers at NASA's Jet Propulsion Laboratory in California sat around their screens and waited. They had sent a sequence of commands to a spacecraft the day before. Not a spacecraft in orbit, not a probe near Mars or Jupiter, a spacecraft traveling through interstellar space more than 15 billion miles from Earth, moving away from us at 35,000 miles per hour. The commands they sent had taken over 23 hours to arrive. Now, watching the data coming back, also taking 23 hours to return, they saw something they genuinely did not expect. The temperature of a set of thrusters that had been considered dead and unusable since 2004 began to rise. Within 20 minutes, the numbers were climbing. The long-dead thrusters were alive. And the engineer who led the My Mission's propulsion team, Todd Barber, said something that has stuck with everyone who heard it. He said, "These thrusters were considered dead, and that was a legitimate conclusion." Then he paused and added, "It was yet another miracle, save for Voyager." That is the story this video is about. Not just the thrusters, not just one fix on one day. The full, unbelievable ongoing story of what Voyager 1 has been going through in the past year, because what NASA has been dealing with, what the spacecraft has been sending back, goes far beyond what anyone in the public has been paying attention to. And when you understand the full picture, all of it, the dead thrusters, the power crisis, the communications blackout, the instrument shutdowns, the maneuver they are calling the Big Bang, and the milestone that is approaching in November that no human-made object has ever reached before, you will understand why the people who work on this mission look at Voyager 1 with something that goes beyond professional respect. They look at it the way you look at something that refuses to die, something that keeps finding a way, something that should not still be here and yet is. Voyager 1 launched on September 5th, 1977. It was designed for a 5-year mission to photograph Jupiter and Saturn. That mission succeeded beyond all expectations. The photographs came back, the science was done, and then the spacecraft kept going. It kept going for another decade while we watched. Then another, then another. In 2012, it crossed the heliopause, the boundary where the sun's influence ends and interstellar space begins, becoming the first human-made object to enter the space between the stars, and it kept going. As of right now, it is over 15 billion miles from Earth. Its signal, traveling at the speed of light, takes more than 23 hours to reach us. Everything you're about to hear has been happening to a spacecraft running on 1970s technology in the dark, billions of miles from anyone who can help it, communicating with home across a delay that makes every crisis agonizingly slow to address. Let us go through what has actually happened in the past year, because the timeline is extraordinary. The first thing you need to understand is the thruster problem, because it was the first crisis of 2025, and it required a repair that the propulsion lead called a miracle. Voyager 1 has a specific set of thrusters responsible for roll control, meaning they keep the spacecraft rotating correctly to maintain its antenna pointed at Earth. Without accurate roll control, the antenna drifts, the signal weakens, and eventually communication becomes impossible. The roll thrusters had been the primary control system for this for decades, but in 2004, 21 years ago, the primary roll thrusters stopped working. A power issue in their internal heaters had rendered them inoperable. Since 2004, engineers had been relying solely on a backup set of roll thrusters to keep the spacecraft oriented correctly. By early 2025, the backup thrusters had a new problem. Residue was building up inside their fuel tubes, the kind of buildup that clogs a thruster and eventually stops it from firing. Engineers estimated the backup thrusters could fail as early as fall 2025. And if the backups failed with the primary thrusters still dead, Voyager 1 would have no way to maintain its orientation. The antenna would drift off Earth. The signal would be lost. The mission would effectively be over. So the team at JPL spent months going back through the engineering documentation of the spacecraft, old wiring diagrams, telemetry archives from the 1970s and 1980s. They were trying to understand exactly why the primary roll thrusters had stopped working in 2004, and one engineer had an idea. What if the heaters themselves had never actually failed? What if a glitch in the power distribution circuitry had simply flipped an internal switch to the wrong position, cutting electricity to the heaters without actually damaging them? If that were the case, a carefully crafted command sequence could potentially flip the switch back, restore power to the heaters, and bring the thrusters back to life. This theory came with a very specific and frightening risk. The thrusters had been cold for 21 years. If the spacecraft's star tracker happened to drift slightly out of alignment while the team was working on the heaters, the onboard software was designed to automatically fire the roll thrusters to correct the attitude. If those thrusters fired before the heaters had warmed them up sufficiently, the result could be a small explosion inside the spacecraft. There was no way to prevent this from happening automatically if the timing was off. The fix had to be executed precisely with the heaters coming back online fast enough that by the time any automatic firing was triggered, the fuel lines would be warm enough to handle it safely. there was also a hard deadline that made everything more urgent. On May 4th, 2025, the Deep Space Station 43 antenna in Canberra, Australia, the only antenna on Earth with enough power to send commands to Voyager 1 at its current distance, was scheduled to go offline for a major upgrade. From May 4th, 2025 through February 2026, that antenna would be out of service for most of that period, with only brief windows of operation in August and in December. If the thruster fix was not completed before May 4th, the team would have no way to attempt it until the antenna came back online in 2026, by which point the backup thrusters could already have failed. The commands left Earth on March 19th. They crossed 15 billion miles of interstellar space at the speed of light and arrived at Voyager 1 more than 23 hours later. The team then waited another 23 hours for the response to come back. Nearly 2 full days of waiting, and then the data arrived. The temperature of the primary roll thruster heaters was rising. Within 20 minutes of the commands executing, the temperature spike confirmed success. The primary roll thrusters, dead since 2004, had been revived from 15 billion miles away. 6 weeks later, the DSS-43 antenna went offline on schedule. Voyager 1 went into its long communications pause with the backup thruster problem solved and the primary thrusters available as a contingency. That was the first unexpected thing NASA was not expecting Voyager 1 to give them. An engineering problem they solved against the clock from interstellar space with a repair nobody had thought possible. But the year was far from over. In February 2026, with the Canberra antenna back online after its 9 months of upgrades, the team performed a routine maintenance maneuver. Voyager 1 periodically rolls to recalibrate its magnetometer instrument, a standard procedure that has been done many times over the decades. On February 27, 2026, during one of these planned roll maneuvers, something unexpected happened. Voyager 1's power levels dropped, not catastrophically, not to zero, but enough to concern the engineers watching the telemetry. The drop was unexpected, unplanned, and not caused by anything the team had done. Engineers quickly realized that any further decline in power could trigger the spacecraft's undervoltage fault protection system, a safety mechanism that would automatically shut down non-essential systems to protect critical ones. They responded immediately. On April 17, 2026, NASA sent a command to deactivate the low-energy charged particle experiment on Voyager 1, an instrument that measures the structure and composition of particles in interstellar space. Turning it off was not anyone's preference. Mission manager Kareem Badruddin said so directly, "While shutting down a science instrument is not anybody's preference, it is the best option available. But the power had to come from somewhere, and the LECP was sacrificed to keep the most critical systems running. After that shutdown, Voyager 1 was left with just 2 operating science instruments, the magnetometer measuring magnetic fields and the plasma wave subsystem listening to the vibrations of interstellar plasma. 2 instruments on a spacecraft that launched with 10. But here's the thing that makes this story not just sad, but extraordinary. Even as instruments were being shut down, the data coming back from those 2 remaining instruments was still scientifically valuable, still revealing things about interstellar space that no other measurement in history had ever detected. The plasma hum, the persistent low-frequency signal of interstellar gas that Voyager 1 first detected back in 2021, continues to be measured. The magnetic field readings continue to map the structure of the ancient interstellar environment that Voyager 1 is moving through. With every passing week, the spacecraft drifts deeper into territory that has never been directly sampled by any instrument ever built, and it is still reporting back. And then, in August 2026, the engineers at JPL attempted something they had been planning for over a year, something they called the Big Bang, not the cosmological event. Their own internal nickname for a power management procedure so delicate, so precisely coordinated that it required shutting down multiple systems and switching in lower power alternatives all at the same time in a single synchronized operation from which there was no going back. The Big Bang was first tested on Voyager 2, Voyager 1's twin spacecraft, which is traveling in a different direction through interstellar space about 13 billion miles from Earth. On August 4th, 2026, the JPL team executed the maneuver on Voyager 2. The procedure involved simultaneously switching off a set of powered devices aboard the spacecraft and substituting them with lower power alternatives that perform the same functions but consume less electricity. The key challenge was thermal. The Voyager probes run on radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. Those generators must not only power instruments and electronics, they must also keep critical components warm enough to function. In interstellar space, if a component cools below its minimum operating temperature, it fails permanently, irreversibly. So the Big Bang had to be executed all at once, not sequentially, because sequential switching would create windows where critical components might cool dangerously before the new, lower power systems had taken over. The announcement came on August 4th. The Big Bang on Voyager 2 had worked. Without that maneuver, Voyager 2 would have been forced to shut down another science instrument before the end of 2026, leaving it with only 2. Instead, all 3 of its remaining instruments will keep running for at least another year. The mission team immediately announced that the same procedure would be attempted on Voyager 1 in the coming months, and if it works on Voyager 1, it may even be possible to restart the low-energy charged particle experiment that was shut down in April, giving the spacecraft 3 functioning science instruments again instead of 2. There is no replacement for what these 2 spacecraft are doing. Let that land for a moment. There is no other mission currently funded, launched, or on a defined development path that can replicate what Voyager 1 and Voyager 2 are doing right now. They are the only in-situ sensor network humanity has ever placed in interstellar space. Every instrument lost from either spacecraft is a measurement that stops forever, a window into the interstellar medium that closes permanently, a type of data that will not be available again for decades, possibly longer. The JPL team knows this. It is why they are willing to attempt a procedure called the Big Bang on a 49-year-old spacecraft running on a power supply equivalent to a dim light bulb. Because the alternative is watching irreplaceable science die. And in the middle of all of this, in November 2026, Voyager 1 is going to do something that no human-made object has ever done. On November 18th, 2026, at 2:16 in the morning Pacific Standard Time, Voyager 1 will be exactly 1 light day from Earth, the first human-made object in history to reach that distance. 1 light day is the distance that light, the fastest thing in the universe, travels in 24 full hours. That distance is approximately 16 billion miles. When a signal leaves Voyager 1 at that moment, it will take exactly 1 full day to reach us. And when we send a response, another full day passes before it arrives. Think about what that means in human terms. If you ask Voyager 1 a question on Monday morning, you get the answer on Wednesday morning. If something goes wrong and you need to intervene, 2 days pass before your intervention reaches the spacecraft. The engineers who manage this mission are essentially doing surgery through a 2-day phone delay on a patient who is flying away from them at 35,000 miles per hour, getting further and harder to reach with every passing hour. And they are succeeding. They are keeping it alive. They are reviving dead thrusters, shutting down instruments to save power, attempting Big Bang maneuvers, and somehow still coaxing science out of a machine that was built when Star Wars was still playing in theaters. The story of Voyager 1 in 2025 and 2026 is not a story about a spacecraft winding down. It is a story about a mission that refuses to accept that it is over. Engineers who refuse to give up, scientists who will squeeze every last watt of power into useful data. A spacecraft that keeps defying what should be its limits, keep going further than anyone planned, keep finding things in the darkness that nobody expected. When that last signal finally comes, when the power finally drops below the minimum threshold for any instrument to function, Voyager 1 will not stop. It will keep flying through the interstellar medium, through whatever lies beyond it into the galaxy, carrying its golden record in the memory of every hand that ever worked to keep it alive. It will pass near a star called Gliese 404.5 in about 40,000 years. By then, the civilization that built it will be unrecognizable. The languages we speak will have changed beyond recovery. Everything we built will be dust. But Voyager 1 will still be out there, still going. The farthest thing humanity ever made, carrying a message in a bottle thrown into the widest ocean there is. And right now, today, it is still talking to us, still measuring, still surprising us, still finding ways to stay alive when every logical expectation says it should have stopped long ago. NASA was not expecting the thrusters to come back. They were not expecting the power drop in February. They were not expecting to still be pulling science out of this spacecraft in 2026, nearly half a century after it left the ground. Let us go even deeper into what this survival story means, because I think most people, when they hear about Voyager 1, focus on the romance of it, the poetic idea of humanity's farthest messenger out there in the dark, and that is real. But there's another dimension that does not get talked about enough, and it is the dimension of what the data Voyager 1 is still collecting actually represents for science. The interstellar medium, the space between the stars, is one of the least understood environments in all of astrophysics. We can observe it from a distance using telescopes, measuring how light from distant stars is absorbed and scattered as it passes through. We can infer things about its density, its temperature, its magnetic field structure, but there is an enormous gap between remote observation and direct measurement. Between seeing something from far away and actually being inside it, measuring it in real time, feeling the plasma waves and the magnetic fields directly with instruments you have placed right in the middle of it. Voyager 1 is the only thing we have ever placed directly inside the interstellar medium, and the data it sends back is not just confirming what we thought we knew. In some cases, it is contradicting it. When Voyager 1 crossed the heliopause in 2012, scientists were surprised to find that the magnetic field direction in the interstellar medium did not match what models had predicted based on remote observations. The density of the plasma was different from expectations. The transition from the heliosphere to interstellar space was messier and more complex than the clean boundary that models had suggested. And the magnetic anomaly that began in 2020, the elevated field readings that persisted for years and that some scientists believe indicate Voyager 1 has entered a pocket of ancient interstellar plasma, is something that no model had predicted, and that is still not fully explained. Every piece of data that comes back from Voyager 1's remaining 2 instruments is ground truth for theories about the interstellar medium that have been built on indirect observation for decades. The magnetometer is still measuring how the magnetic field around the spacecraft changes as it moves deeper into interstellar space, providing a running map of the magnetic environment at the very local scale that remote observations can never achieve. The plasma wave subsystem is still listening to the hum of interstellar plasma, the continuous low-frequency signal of ionized gas vibrating in the vacuum, giving scientists their only real-time measurement of plasma density in the space Voyager is currently crossing. These are not routine measurements. They are the only measurements of their kind anywhere in the known universe. Every single data point is irreplaceable, and the people at JPL know that shutting down even one more instrument represents a permanent loss that no future mission can recover for decades. That is part of why the Big Bang maneuver matters so much beyond just keeping the spacecraft alive. The success on Voyager 2 means that the same technique will be applied to Voyager 1. And if it works on Voyager 1, the mission team believes that not only can they prevent losing another instrument, they may actually be able to restart the low-energy charged particle experiment that was shut down in April, turning a lost instrument back on, getting 3 instruments instead of 2, buying more time, more data, more science, from a spacecraft that has been exceeding its expected lifetime by more than 4 decades already. There's also the communications picture to understand because it affects everything about how this mission is managed. As of August 2026, Voyager 1 is around 15.8 billion miles from Earth. The one-way communication delay is over 23 hours, but that distance is not fixed. It is increasing. Every year that passes, Voyager 1 is further away. Every year, the signal it sends back is slightly weaker when it arrives. Every year, the Deep Space Network antennas on Earth have to work slightly harder to pick it out of the background noise of the universe. The 230-foot antenna at Canberra that just came back online after its long upgrade is part of an ongoing effort to keep the ground infrastructure capable of maintaining contact as the spacecraft moves into distances that have never been attempted before. By November 2026, when Voyager 1 reaches 1 light day from Earth, the signal will be so faint that the antenna in Canberra is essentially operating at the limit of what is physically possible with current technology. There is no larger antenna already built that could take over. The Deep Space Network is the best we have, and Voyager 1 is approaching its maximum range. Future improvements in signal processing and antenna technology may extend communication slightly further, but there will come a point where the signal drops below the noise floor permanently and irretrievably. Nobody knows exactly when that will be, but it is not far off on any reasonable timescale. This is what gives the current moment in the Voyager story its particular urgency. Every instrument that stays online right now matters more than it would have 5 years ago, because there are fewer years left. Every data point collected today is a data point that would not have existed if the team had given up last month or last year or in 2023 when the communication crisis nearly ended the mission entirely. The people who work on Voyager are racing time itself, not in a dramatic Hollywood way, but in the quiet, methodical, deeply skilled way that real engineers and scientists work against limits that cannot be moved, only managed. They cannot make the power last forever. They cannot make the signal stronger than physics allows. They cannot make the spacecraft younger. All they can do is be smart about how they manage what remains, and they have been extraordinarily, almost incomprehensibly smart about it. Dead thrusters revived after 21 years, a memory chip repaired from 15 billion miles away by scattering code across different memory locations, like hiding chapters in different rooms of a house. Instruments sacrificed in the right order to keep the most valuable ones running. Power procedures nicknamed the Big Bang executed simultaneously on aging systems, where a single wrong move could trigger a cascade failure. Voyager 1 keeps surviving because the people who work on it refuse to give up on it, and that refusal is backed by genuine expertise, decades of accumulated knowledge about a specific spacecraft that no one else on Earth understands the way they do. When Todd Barber said these thrusters were considered dead, and that was a legitimate conclusion, what he meant was the evidence said they should not work. The rational conclusion was that they were gone. And then one engineer asked one question, followed one thread of logic to one possible cause, and it turned out the rational conclusion was wrong. And that is why you keep asking questions, even when you think you know the answer. Science and engineering at their best are the same thing. The willingness to test assumptions, the willingness to be surprised, the willingness to send a command into the darkness, wait 46 hours for a round-trip response, and hold your breath until the data comes back. Voyager 1 One just sent back something NASA was not expecting. It sent back the message that it is still alive, still functioning, still finding ways to keep going into territory that no other human artifact has ever explored. That is not what anyone planned for in 1977. It is not what the mission was designed to deliver. It is just what happened when a spacecraft that was built to last 5 years turned out to be built better than anyone knew and was maintained by people who refused to accept that it was finished. On November 18th, 2026, a signal will leave a spacecraft traveling through the darkness between the stars and spend exactly 24 hours crossing the void before it reaches Earth. Voyager 1 will be one light day away, the farthest human-made object in history, still transmitting, still surprising us, still, after 49 years, finding things NASA was not expecting. That is what Voyager 1 does. That is what it has always done, and for as long as there is a signal coming back, that is what it will keep doing.